Bismillahirrahmanirrahim. In this session, we will discuss half-life, and for this half-life, this nuclear stability is very important. The stability of a nucleus depends on both the number of proton and the number of neutrons. So this is the figure, and this is the stable line. It means that the number of neutrons is more than the number of proton. So at this point, figure 5.210 is a plot of N against V for all non-nucleides. The blue band indicates the region over which the stable nucleides occur. So this blue band region is the stable nucleides are placed. The continuous line drawn through the center of the band is called the stability line. This line is the stability line, and it's found that for stable nucleides, for light nucleides, N is equals to Z. So for this number, for 20 is 20. And similarly, with the increasing number of Z, the N is increases. So N is increases for the heaviest atom. Most nucleides have even N and Z, implying that a particle combination of 2 neutrons and 2 protons is likely to particularly stable. For unstable nuclide, the disintegration tend to produce new nucleides nearer the stability line. In that stability line region, and new nucleides are formed until a stable nuclide is formed. A nuclide above the stability line decreases by above the stability line, it decays this beta emission. Below this, alpha and other emissions. So nucleides below the stability lines, beta plus minus emission for a proton change to neutron, and the ratio decreases and increases. So here beta emissions, here beta positive emission, proton change to neutrons. So this is half-life. The radioactive atoms have unstable nuclei which changes or decay to atoms of different elements when they emit alpha beta particles. So the result of this alpha and beta emission, the atom changes to different elements. So different elements are formed. The rate of decay is unaffected by the temperature, but every radioactive element has its own definite decay rate expressed by its half-life. The half-life of a particular isotope is the time taken for half of the nuclei of that isotope is in a given sample to decay. So this is a probabilistic phenomena, but see, this is defined in terms of its expected value. So it is difficult to know when the substance has lost its radioactivity, but for the time for its activity to fall to half, its value can be found more easily. So radioactive decay curve. So this is a radioactive decay curve. With the time, this radioactivity disintegration occurs. Suppose this 80 disintegration per second to 40 disintegration per second after 10 minutes, and after 20 minutes, after 30 minutes. So after 10 minutes, from 80 to 40, so this disintegration has decreased to half, from 80 to 40. From 80 to 40 to 20, it's again decreases to half. From 20 to 10, it again half. So this 10 minutes is basically the half-life of this radioisotopes. So for radium, this half-life value is very large, 16 100 years. And some isotopes have a half-life in terms of seconds or milliseconds. This information for this figure 5.1211, time t is equal to 0, the counts was 80, at 10 minutes the count was 40, at 20 minutes the count was 20, after 30 minutes the count was 10. So this was plotted here. So the half-life is basically the 10 minutes, because after 10 minutes the counts decrease to its half value. Now put this into practice. So this is an experiment to find the half-life of radioisotopes. The following results were obtained. At zero time, the count was 200. At 10 it was 133. At 20 it was 88. 30 it was 59. At 40 it was 39, and at 50 it was 26. So after one half-life, this 200 will decrease to 100, and this 100 will decrease to 50, and this 50 will decrease to 25. So this shows that this values nearer to 25. So this is basically 3 half-life. So from here to here, it has 3 half-life. Let's approximate this 3 half-life as a 51 minutes. So this 1 half-life is basically 51 upon 3 minutes. So this is 17 minutes. So from this value, it shows that 17 minutes is the half-life of these radioisotopes, because after 3 half-life, this 200 decreased to 100, and 100 to 50, and then 50 to 25. So this is very close to 25. So we assume that after 51 minutes it becomes 25. So this 3 half-life gives 51 minutes. So 1 half-life is basically 17 minutes. This is plotted here. This is 200. This is 150, and this table is plotted on this experiment. From this graph we can see this at this 50 it is the second half-life, at 100 first half-life, which is 10, 15, and this is 17, and this is 34 at this value. So this is simple graph. Very important question. Radioactive source has a half-life of 15 minutes. Find the fraction left after 1 hour. So half-life is 15 minutes. So time elapsed is 1 hour. So number of half-life is equal to time elapsed divided by half-life. So half-life is 15 minutes and the time elapsed is 1 hour. So this is 4. So after 15 minutes, 1 half-life will go. So there are 4 half-lives are there. So 1 over half power 4 is 1/16. So the radioactive source will decrease to 1/16, 1/16 activity. The fraction will left with 1/16. In an experiment to determine the half-life of a radioactive material, its count rate falls from 140 counts per minute to 35 counts per minute in an hour. Calculate the half-life of the material. So initial count was 140 counts per minute. Final counts was 35 counts per minute. Time elapsed is 1 hour. So number of half-life. So the final count was and the initial count. So this is the ratio of initial and final count is half 1/4. So 1/2 power 2. So 2 half-lives is equal to 60 minutes. So half-life of the material is 30 minutes. So after half-life, 1 half-life, this 140 will counts down to 70 counts per minute, and then second half-life, the 70 downs to 35 counts per minute. So the half-life is basically 30 minutes. Carbon-14 has a half-life of 5700 years. A 5-gram sample of wood cut recently from a living tree has an activity of 80 counts per minute. This is 80 counts per minute. A 5 grams piece of wood taken from an ancient dugout canoe has an activity of 20 counts per minute. Estimate the age of the canoe. Carbon-14 half-life is 5700 years. 5 grams wood activity is 80 counts per minute. Activity wood is 20 counts per minute. So taken from this canoe, this is 20 counts per minute. So 20 counts per minute divided by this 80 counts per minute is equals to 1 by 4. So this is equals to 1 by 2 power 2. So one half-life is 5700 years. So two half-life is 11,400 years. So the age of the canoe is 11,400 years. Again, in this test yourself problem on page 271, in an experiment to determine the half-life of a thorium, the following results were obtained. Time at t is equal to 0, 165 counts, 30 seconds, 112, and at 180 seconds the count was 20 counts per second. So the count was given this, and the total background count was found to be 5 counts per second. So we will subtract these 5 counts, and these corrected counts are given as 160, 107, 72, 48, and then this 15. We know that after 160 to 20, 3 half-life will elapse. So estimated time is approximately 20. It will be in the range of 159. Assume that at 159, between this range, its value will be around 22 to 20, lies between in this range. So 159 seconds takes 3 half-life. So one half-life is basically the 53 seconds or 54 seconds. It's very close. A plot of the corrected counts against time and estimated half-life of thorium. So this is the count rate, this and this value is plotted. This is on the y-axis and this time is on the x-axis. This corrected counts, and it is plotted here. 160 at 0 second, and this is 30 at this seconds. This much count at 30 seconds, count this is 60 seconds. So this table is this first row and third row is plotted on this graph. The half-life of the radioactive gas is 2 minutes. The half-life of this radioactive gas is 2 minutes. The time elapsed, then after 8 minutes, the activity will have fallen to a fraction of its initial value. So we have to find the what fraction of this radioactive gas will remains there. The number of half-life from 8 minutes to 2 minutes is 4. So 4 half-life is passed. So the fraction will reduce to 1 over half, like power 4. So 1 over 16. So this will reduce to 1 over 16. So this D part is correct. In the next session, we'll discuss this uses of radio.